Okay, so what we have today is number 57 on the inertia problem set that we have here. And the given situation is that we have this soup can of mass of 0.215 kilograms. I just converted this for us. And it's rolling down this hill that is 3 meters long, and it takes 1.5 seconds to do this. And what it's asking for is, what is this moment of inertia that requires this can to be able to roll down this hill? And this is actually pretty convenient, because then we don't actually have to look up this actual formula for the specific moment of inertia of the can, because we're actually solving for this right now. And it could be anything, really. It could be like some weird object, because we're given this kind of data. Now, what we do need to know is, of course, we can use conservation of energy, because this potential energy right here is all going to be converted to some sort of it's going to disperse to both kinetic and inertial energy. So what we can say here is actually this potential energy, right? That's going to turn into both kinetic energy plus the rotational energy, the kinetic rotational energy that requires to actually move that can around, because there's rotational energy that needs to be used to rotate this can around. So this, using what we know, of course, that actually can be said that mgh, that's going to be equal to 1/2 mv squared plus 1/2 I omega squared. And of course, now we have an issue. I mean, we don't have omega. But that's simply easy, because actually the reality is we know how far it's going, which is 3 meters, and how much time it took, which is 1.5 seconds. So we can actually get the actual angular analog of velocity, omega, by using what we know. Well, we know that this actual speed, that's actually going to be equal to omega times the radius. And we know the radius is 0.0319 meters after the conversions. It's really omega. That's this velocity over r. And that's going to be, so we're going here, so it's going to be 3 meters divided by 1.5 seconds over 0.0319 meters. And after using the calculator, so that's going to be 3 divided by 1.5 seconds divided by 0.0319. That's 62.7 rads per second. So 62.7 radians per second. And of course, radians is, of course, another counting unit for, in another hand from the degree. It's just another counting unit. So 62.7 radians per second. This is going to be our omega, so we know that we can actually be able to find our inertial force. Everything else we're able to find here. So, for example, we know this height because we're given this 25 degree, and then we have 1.5 seconds. We can just use, of course, our simple trig, where we say, of course, okay, so the sine of 25, of course, degrees, that's going to be equal to x over 3. So we know this is really just 3 sine 25 degrees, this height. Then, of course, we can say, okay, so what we want is I, right? So, okay, so we can say mgh, that's equal to 1/2 mv squared. Well, actually. So then we have 1/2 inertia omega squared. So with m, g, and h, we know that actually m is going to be 0.215 kilograms times 9.8 meters per second squared, and of course 3 times sine of 25 degrees. And make sure that you're in radian mode too, because or else that might just screw you over on the answers. So by plugging for the actual results here, we're given that it's 2.67 joules. That's going to be equal to the kinetic energy plus the rotational energy, right? So this rotational energy, that's going to be equal to 2.67 joules minus the kinetic energy, which is 1/2 mv squared. If they're plugging in for 1/2 mv squared, that's going to be 0.5 mass, 0.215 kilograms. And then for V, well, we can just use 3 divided by 1.5 seconds squared. So that's going to be 2.67 joules minus 0.43 joules. And that's going to be equal to 2.24 joules. So we know that 1/2 I omega squared is equal to 2.24 joules. Then we can solve for I by saying, okay, well, therefore, that's going to be equal, this I, that's going to be equal to 2 times 2.24 joules over omega squared. We can plug in for squared, which we solve for right here, which is 62.7 radians per second. So then by putting that in, we can say 2.24 joules divided by 62.7 squared. We get 0.0011 0.00114, and then for the units, what we're going to end up doing is we say, okay, so that's joules per rads per second squared. Yeah, per rads per second. And there we go.